Okay, so we're going to start the second part of 12.6 with the exercises from the last video. And so this, if you fix a couple of values here, so say 0 and plus or minus 6, we get 4y squared plus 9z squared equaling 0, which means y and z must be 0. And if you plug in plus or minus 6 and you simplify, you'll get y squared over 9 plus z squared over 4 is equal to 1. Because you'll get 36 on one side, you divide both sides by 36 to get this elliptical equation. So what happens is you, for x equaling 0, you just have a single point, which is 0, 0, 0. But say for plus and minus 6, you end up with ellipses that are a little bit more stretched in the y direction than in the z direction. And so you get this cone that is opening in the plus and minus x direction. For the second one, which is y equals 4 minus 2z squared, well, in the yz plane, you just have a parabola. So here's y, here's z, and z is 0, you have y equals 4, and you have a negative pointing parabola, something like this. And here x is free. So for every x value, you get a copy of this. So for example, you'll have repeated ones, and all the parabolas here will be connected like so. So you get this. I guess I don't really need this part, but you get this what we call parabolic cylinder, because it's just copies of that parabola over and over and over. Okay, so those were the exercises from last time. What we're going to do is we're going to talk about the next category of graphs, which is the paraboloid. An example of that would be something like this, where z is now in a single power, and you have something in x squared plus something in y squared. And notice here that z must be at least 0 because x squared and y squared are always positive. So we can't plug in any z values less than 0. So let's fix some z values, see what happens. Let's plug in, say, 0, not plus and minus, but just plus 4. 4 and let's say 16. So here we get 4x squared plus y squared equals 0, so x and y must be 0. Here we get, let's see, we get x squared plus y squared over 4 is equal to 1. And here we get x squared over 4 plus y squared over 16 is equal to 1. So we have elliptical cross sections here, and we'll see why it's called a paraboloid though in a second. So let's draw our points. At 0, we have 0, 0, 0. At 1, we have an ellipse that's stretched out a bit more in the y. And at 16, somewhere up here, we have another ellipse. How are these connected? Well, let's set x to be 0. What do we get? We get z equals y squared, which is the parabola, and hence the paraboloid. And what that does is that connects these guys together into a single, kind of like a bowl. Think of this, this is basically a bowl. Put some milk and have some cereal. That's pretty much your paraboloid. Okay, so that's an example of the paraboloid graph. The next example that we have is what's called a hyperboloid. And there's two types here. There's a hyperboloid of one sheet and the hyperboloid of two sheets. So the hyperboloid of one sheet, we'll see why these names are there. I'm giving kind of relatively simple examples. For each of these, you can always modify these to make it a bit more complicated, but these suffice for giving the idea. Now what I want to do is first write down both equations so you see the difference here. Here there are two positive square terms, and here there are two negative square terms. along with a positive constant. So that kind of distinguishes algebraically the two features. Let's see why the first one is called hyperboloid of one sheet. So let's start with the first example here. Let's fix some z values. So if I have z equals 0, let's do z equals, I don't know, 2 and negative 2, because those both will give you the same thing. Let's do maybe one more, say 3 and negative 3. Here you'll get x squared plus y squared is equal to 4. Here you'll get x squared plus y squared is equal to 8. Here you'll get x squared plus y squared is equal to 13. So the cross sections here are circular, so that well, at z equals 0, we have a circle of radius 2. At plus and minus 2, we have a slightly larger circle. And at plus or minus 3, you'll have yet a slightly larger circle. Now, how do these connect? Well, let's set x to be 0. So we have y squared minus z squared is equal to 4. And this is an equation of a hyperbola. Hence the hyperboloid concept. So what this does is in the yz plane, you have these hyperbolas. And this is the hyperboloid of one sheet. It's one giant sheet. And that's how that goes. Contrast that with the following example. This is going to be split into two parts, hence the two-sheet idea. Also, it's going to be different. This kind of opens out in Z. The first example here, so this guy opens kind of up and down, right, along the Z. Whereas this guy, we'll see that this actually opens along X. Okay. Let's see how that goes. So let's note that if you plug in first 0 or like plus or minus 1, you end up with the following equations. So these equations, well, they have no solutions because you have a negative number equaling a positive number. So there's no graph here, basically. No graph or no solutions. You need at least to get up to plus or minus 2 to get negative y squared minus z squared is equal to 0, which means y and z must be 0. So you have these kind of vertex points, if you will, it's 2, 0, 0, and negative 2, 0, 0, that are going to be part of the graph. And as you keep going, say I plug in plus or minus 3, I'll end up with negative y squared minus z squared is equal to negative 5, or y squared plus z squared is equal to 5. So you have a circular cross-section along the planes x equals plus and minus 3. And that continues to be the case. If you say plug in plus and minus 4, you'll get negative y squared minus z squared is equal to 4 minus 16, which is negative 12, or y squared plus z squared is equal to 12. So you're going to get circular cross-sections as x grows in absolute value. So what ends up happening here, and let me just keep the equation here so we have that available for us, that in the x direction now, at plus and minus 2, we have just points. And as we go along in 3, at x equals 3, you'll have a circle. At x equals negative 3, you'll have a circle. At x equals 4, you'll have a slightly larger circle. At x equals negative 4, you'll have a slightly larger circle. And so, but how do these connect? Let's set z to be 0 and see what happens. We get x squared minus y squared is equal to 4, which is the equation of a hyperbola. So in the xy plane here, you have a hyperbola that's opening out. So these actually connect. These circles that we've drawn connect via a hyperbola. and hence you have the hyperboloid of two sheets. Because there's a split, there's a gap in between, which wasn't there for the hyperboloid of one sheet. All right, last example here before we conclude. This has a kind of fancy name. It's called a hyperbolic paraboloid, but I like to call it a saddle graph, just because it's a little bit easier to remember, because the terminology can get kind of confusing. How is this a saddle? Well, let's fix some values. Let's fix x equals 0. Actually, you know what? Let's fix y equals 0 first, so that we get y equals z equals x squared plus 1 in the zx plane. So here's z, here's x, and we have a parabola opening upward. That's z equals x squared plus 1. If we set some x values, if x is 0, we get z equals 1 minus y squared. If we set x to be plus or minus 1, we get z equals 2 minus y squared. Let's just plot those, and we'll plot those in red. So for x equals 0, in the zy plane here, we have a parabola pointing downward. Similarly, at 1 and negative 1, we have parabolas pointing downward. And so what you see here is, I hope you can kind of see the saddle forming. That, for example, if you were going to sit here, and I'll put an arrow where you would be sitting. You'd be sitting right there. Your legs, so the legs would be along the red lines, the red traces, which are the, when you're fixing x values, it'll be parallel to those, basically. And that's kind of how the saddle terminology comes to play there. But again, if you want to see a little bit better version of this graph, I can draw more traces here, but it'll probably ruin what is at least an okay graph. So I definitely urge you to try to look up this graph on GeoGebra if you want to see the full saddle. Okay, I'll leave you here with a couple of exercises. So one is graph z equals 8 minus x squared minus y squared. And the second one is x squared plus y squared minus z squared is equal to minus 3. And I'll give you a little hint is to bring the constant to the left-hand side, LHS left-hand side, and bring the variables to the right-hand side. So it matches up with kind of a pattern which I mentioned a little bit earlier in one of these graphs. And then I would say fix some z values. And that'll probably do you well. Okay, we'll stop here. We'll start 13.1 in the next video.